Imagine a robot gets injured on the battlefield or in deep space. It's artificial muscle tears. Normally, it would shut down or need a human to repair it. But what if, just like us, it could heal itself? Sounds like science fiction? Well, it's not. Engineers have just brought science fiction one step closer to reality. Today, we're diving into one of the craziest breakthroughs in robotics: self-healing artificial muscles. Yes, robots that can bleed, repair, and keep on moving. But how do you get metal and wires to behave like living tissue? What does healing even mean for a machine? And are we on the verge of creating machines that are, well, almost alive? Stick around, because what you're about to learn will completely change how you think about robotics, biology, and the future of machines. Robots are incredible. They build our cars, explore Mars, and dance better than most of us. But here's the truth. They're fragile. One torn cable, one snapped actuator, and the robot's down. No pain receptors, no immune system, no way to fix itself. Biological creatures, even simple ones, heal. You cut your finger, a few days later, good as new. Robots? They rely on technicians, spare parts, and downtime. That's where this new breakthrough comes in. In a lab in the Netherlands, engineers created an artificial muscle made from a special polymer material that can stretch, contract, and crucially, heal itself. It's called a self-healing elastomer, a rubbery material that mimics real muscle tissue. If it gets cut or punctured, just add a little heat, and the material bonds back together. We're talking 90% strength recovery in under 24 hours. Some materials even heal without heat, automatically fusing in minutes. Think of it like Wolverine, but synthetic. So how does this magic work? It comes down to chemistry. These polymers have something called reversible bonds, basically molecular Velcro. When a material gets damaged, the bonds break. But under the right conditions, like heat or pressure, the molecules reconnect. Some teams are also experimenting with ionic liquids and hydrogels that mimic the softness and healing ability of living tissue. The result? A material that's soft, flexible, and can power artificial muscles, while fixing itself if it gets torn or overextended. This isn't just about cool materials. Imagine robots that explore disaster zones and heal from debris damage. Soldiers wearing exosuits that recover overnight after a tough mission. Or even prosthetic limbs that repair themselves, giving amputees more reliability and freedom. It's a game changer for longevity, autonomy, and safety in robotics. Even NASA's interested. Why? Because if something breaks on Mars, there's no workshop to fix it. Self-healing tech could mean robots that survive the unforgiving extremes of space. Today it's elastomers. Tomorrow, it might be biohybrid robots, where living cells are grown on machines. Researchers are already blending lab-grown muscle with robotics, creating machines that behave more like animals. We're entering an era where the line between machine and organism begins to blur. Will robots feel pain? Will they know when they're hurt? Will they one day heal emotionally? Okay, maybe that's a stretch. But one thing is clear. The future of robotics is going to look and heal a lot more like us. A University of Nebraska-Lincoln engineering team is another step closer to developing soft robotics and wearable systems that mimic the ability of human and plant skin to detect and self-heal injuries. Engineer Markvicka, along with graduate students Ethan Krings and Patrick McManigal, recently presented a paper at the IEEE International Conference on Robotics and Automation in Atlanta, Georgia, that sets forth a systems-level approach for a soft robotics technology that can identify damage from a puncture or extreme pressure, pinpoint its location, and autonomously initiate self-repair. The paper was among the 39 of 1,606 submissions selected as an ICRA 2025 Best Paper Award finalist. It was also a finalist for the Best Student Paper Award and in the Mechanism and Design category. The team's strategy may help overcome a long-standing problem in developing soft robotic systems that import nature-inspired design principles. Engineer Markvicka, along with graduate students Ethan Krings and Patrick McManigal, recently presented a paper at the IEEE International Conference on Robotics and Automation in Atlanta, Georgia, that sets forth a systems-level approach for a soft robotics technology that can identify damage from a puncture or extreme pressure, pinpoint its location, and autonomously initiate self-repair. The paper was among the 39 of 1,606 submissions selected as an ICRA 2025 Best Paper Award finalist. It was also a finalist for the Best Student Paper Award and in the Mechanism and Design category. The team's strategy may help overcome a long-standing problem in developing soft robotic systems that import nature-inspired design principles. In our community, there's a huge push toward replicating traditional rigid systems using soft materials, and a huge movement toward biomimicry, said Markvicka, Robert Van Myrna L., Krohn Assistant Professor of Biomedical Engineering. While we've been able to create stretchable electronics and actuators that are soft and conformal, they often don't mimic biology in their ability to respond to damage and then initiate self-repair. To fill that gap, his team developed an intelligent, self-healing artificial muscle featuring a multi-layer architecture that enables the system to identify and locate damage, then initiate a self-repair mechanism, all without external intervention. The human body and animals are amazing. We can get cut and bruised and get some pretty serious injuries. And in most cases, with very limited external applications of bandages and medications, we're able to self-heal a lot of things, Markvicka said. If we could replicate that within synthetic systems, that would really transform the field and how we think about electronics and machines. The team's muscle, or actuator, the part of a robot that converts energy into physical movement, has 3 layers. The bottom one, the damage detection layer, is a soft electronic skin composed of liquid metal microdroplets embedded in a silicone elastomer. That skin is adhered to the middle layer, the self-healing component, which is a stiff thermoplastic elastomer. On top is the actuation layer, which kickstarts the muscle's motion when pressurized with water. To begin the process, the team induces 5 monitoring currents across the bottom skin of the muscle, which is connected to a microcontroller and sensing circuit. Puncture or pressure damage to that layer triggers formation of an electrical network between the traces. The system recognizes this electrical footprint as evidence of damage and subsequently increases the current running through the newly formed electrical network. This enables that network to function as a local joule heater, converting the energy of the electric current into heat around the areas of damage. After a few minutes, this heat melts and reprocesses the middle thermoplastic layer, which seals the damage, effectively self-healing the wound. The last step is resetting the system back to its original state by erasing the bottom layer's electrical footprint of damage. To do this, Markvicka's team is exploiting the effects of electromigration, a process in which an electrical current causes metal atoms to migrate. The phenomenon is traditionally viewed as a hindrance in metallic circuits because moving atoms deform and cause gaps in the circuit's materials, leading to device failure and breakage. In a major innovation, the researchers are using electromigration to solve a problem that has long plagued their efforts to create an autonomous, self-healing system, the seeming permanency of the damage-induced electrical networks in the bottom layer. Without the ability to reset the baseline monitoring traces, the system cannot complete more than one cycle of damage and repair. It struck the researchers that electromigration, with its ability to physically separate metal ions and trigger open circuit failure, might be the key to erasing the newly formed traces. The strategy worked. By further ramping up the current, the team can induce electromigration and thermal failure mechanisms that reset the damage detection network. Electromigration is generally seen as a huge negative, Markvicka said. It's one of the bottlenecks that has prevented the miniaturization of electronics. We use it in a unique and really positive way here. Instead of trying to prevent it from happening, we are, for the first time, harnessing it to erase traces that we used to think were permanent. Autonomously self-healing technology has potential to revolutionize many industries. In agricultural states like Nebraska, it could be a boon for robotic systems that frequently encounter sharp objects like twigs, thorns, plastic, and glass. It could also revolutionize wearable health monitoring devices that must withstand daily wear and tear. The technology would also benefit society more broadly. Most consumer-based electronics have lifespans of only 1 or 2 years, contributing to billions of pounds of electronic waste each year. This waste contains toxins like lead and mercury, which threaten human and environmental health. Self-healing technology could help stem the tide. So, what do you think? Should we make robots more like living creatures, or are we playing with fire? Let us know in the comments. And hey, if this blew your mind, hit that like button, share with a friend, and subscribe for more weekly deep dives into the future of tech and science. This is Random and Boring TV, where the machines aren't just rising, they're healing.